Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review as covered in week 5. Now, since we've already completed our first topic, I thought for this video I'd go through some common mistakes that I've seen. So the first mistake, thinking that an answer is negative if any of the numbers in a product or quotient are negative. Yeah, that makes it sound really complicated. Just remember, product means times, quotient means divide. What I'm saying here is people sometimes will get something like -7 times -4, and because there's negatives in the question, they think the answer must be negative, here -28. But we know better. We know that two negatives multiplied together or two negatives divided by each other yields a positive answer. The answer is only negative if one of the numbers is negative. So -36 divided by 4, for example, would be a negative. So, if you multiply two negatives or divide two negatives, you get a positive answer. If you multiply two numbers or divide two numbers and only one is negative, then the answer is negative. All right, let's move on to the next mistake. So the second mistake is thinking that adding two negatives makes a positive. I sort of understand where this is coming from. See, on the previous slide, we did things like -3 times -8. When you multiply or divide two negatives, the answer is positive, but it's not actually the same for addition and subtraction. Let's say we're adding -5 and -12. So here I'm adding a negative and a negative. My answer is not positive. That rule only works for multiplying and dividing. When we're adding or subtracting directed numbers, what we do is we look at the sign between the two numbers. So when you have a plus and a minus next to each other, it becomes a minus. So when we have something like -7 subtract -3, if we have two negatives here next to each other, it's not the answer that's positive, it's the sign between them that becomes positive. So when we add or subtract directed numbers, we reduce it so we're subtracting a positive number or adding a positive number. And this is another mistake that comes up. When you subtract a positive number, your answer must be less than what you started with. Some people do -5 minus 12 and they'll get a number that's way more than -5. Of course, if you subtract 12 from any number, you reduce that number. So -5 minus 12 is actually -17. And -17 is a lot smaller than -5. So similarly, when we're adding a positive number, here we're adding 3, we make the number larger. A lot of people will say that -7 plus 3 is -10. But that doesn't make any sense. -10 is less than -7. You can't add 3 to a number and make the number smaller. So -7 plus 3 is -4. So in both cases, we ended up with a negative answer. So the rules for multiplying and dividing don't apply to adding and subtracting. When we multiply and divide, we think about whether the answer is positive or negative. When we're adding or subtracting, we think about whether the sign between the two numbers is a subtraction or addition. All right, let's move on now to some fractions. So the next mistake is that when people are multiplying or dividing fractions, they think they have to make the denominators equal. And that's not true. You only have to make the denominators equal when adding or subtracting. So what people will do in this situation is they'll find the lowest common denominator, so multiply top and bottom of the first fraction by 5, top and bottom of the second fraction by 3, and then you get 10 over 15 times 12 over 15. And then people don't know, are they supposed to multiply the denominators? What do you do now? So this making the denominators equal when multiplying or dividing fractions, it actually isn't wrong, it just makes it so much harder. So if I went ahead and did this, 10 times 12 is 120, 15 times 15 is 225. You get the right answer, but it's not simplified. This requires a lot of simplifying. In fact, you'd have to divide top and bottom by 15. So that actually takes quite a bit of work. Why don't we just do it the proper way? Multiplying fractions is actually pretty easy. All you do is multiply the tops, multiply the bottoms, and simplify if you need to. So see how we got the same answer here, but this one took a lot more steps and a lot more brain power. So similarly for dividing, we don't make the denominators equal. All we do is flip the second fraction and make it a times. Then we have 2 times 5 over 3 times 4, and sometimes you need to simplify. Don't make the denominators of fractions equal when multiplying or dividing. All right, let's look at a similar mistake now. So the next mistake is people not making denominators equal when adding or subtracting fractions. So sometimes people will get something like this, 1 over 2 plus 1 over 3. They'll just add the tops and add the bottoms. This is wrong. You don't need to make denominators equal when multiplying or dividing, but you must do so when adding or subtracting. So 1 over 2 and 1 over 3, you're sort of comparing different things, halves and thirds. So what we need to do is make them common so we can compare them. When I say make them common, they have to have the same denominator. So what you do is you make a half and a third have the same denominator here. So which denominator should we pick? What should we change the denominator to? The answer to that is the lowest common multiple of 2 and 3. Now, people always get mixed up between lowest common multiple and highest common factor. The lowest common multiple of 2 and 3 is going to be bigger than those numbers. It's the lowest number divisible by 2 and divisible by 3. So that means it's going to be 6. 6 is the lowest number that's divisible by 2 and also divisible by 3. Notice that 6 is larger than these two denominators. When you're finding the common denominator, you're always making it bigger than at least one of the denominators. So how did I get from 2 to 6? I multiplied by 3. Golden rule of fractions, what you do to the bottom, you must do to the top. What you do to the top, you must do to the bottom. So a half is the same as 3/6. A third is the same as 2/6. Now that we have these two fractions having the same denominator, we only add the numerators. We only add the tops and we keep the same denominator. We never add or subtract the denominators. All right, let's look now at a mistake involving mixed numbers. So the next mistake I see is a common one when trying to multiply or divide mixed numbers. So these are both mixed numbers because they have an integer, a whole number part, and a fraction. Now, when people get something like this, they try to do all kinds of weird things. They try to go 2 times 3 plus a half times a third. It just doesn't work that way. What you need to do when operating with mixed numbers, so that's adding, subtracting, multiplying, and dividing mixed numbers, you need to make them into improper fractions. So to make 2.5 into an improper fraction, 2 times 2 is 4, plus 1 is 5, and we always keep the same denominator. 3 1/3. 3 times 3 is 9, plus 1 is 10, and we keep the same denominator. So now, when I'm multiplying these numbers, 5 times 10 is 50, 3 times 2 is 6. So we can simplify this to 25 over 3. Now, really important here, when you're operating with mixed numbers, it's not considered simplified to give your answer as an improper fraction. You must give it as a mixed number. So to convert from an improper fraction to a mixed number, we just divide. 25 divided by 3. So 3 goes into 25 8 times, so the 8 goes there, but there's one remainder. So the remainder goes up here, and we keep the same denominator. Okay, so whenever you're operating on mixed numbers, always first convert to improper fractions, and if your answer is an improper fraction, convert back to a mixed number. All right, let's look at some mistakes involving decimals. So the next mistake is not having enough digits after the decimal point in the answer when multiplying decimals. So if you have something like 0.12 times 0.06, what you do is just multiply the numbers as if there's no decimal point. So 12 times 6 is 72. Now we need to count how many digits after the decimal place our answer should have. In the question, there are 1, 2, 3, 4 digits after the decimal point. So our answer has to have 4 digits after the decimal point. So if I put the decimal point here, obviously we have a problem. We only have 2 digits. So in that case, you need to add in zeros. So 0.12 times 0.06 is 0.0072. Notice 1, 2, 3, 4 digits after the decimal point. All right, let's look at another mistake involving decimal multiplication. So the next mistake is not using long multiplication when needed. So in the last one, the last decimal multiplication was just 6 times 12. We know that's 72. But here, when we're multiplying these decimals, we're going to multiply them with no regard for the decimal place. We actually have to multiply 102 and 71. This is how I want you to do it. People get a question like this and they try to do all sorts of weird things. 10 times 7 plus 0.2 times 0.1 or whatever. Don't do it. Just use long multiplication. We're going to multiply these numbers without regarding their decimal place, 102 times 71. Then we're going to count how many digits should occur after the decimal place in our answer. So let's use some long multiplication, because 102 times 71 we probably can't do in our head. So we go 1 times 2 is 2, 1 times 0 is 0, 1 times 1 is 1. So we've just done 1 times 102. Now we don't do 7 times 102, we do 70 times 102. So we need to put a 0 here because it's 70 times 102. So then we go 7 times 2 is 14. So then we're going to carry the 1. 7 times 0 is 0 plus 1 is 1. And then we go 7 times 1. So now we add together these two. 2 plus 0, 0 plus 4, 1 plus 1, and 7 plus 0. So 102 times 71 is 7,242. Now we decide how many decimal places are needed in our answer. So the question had 2 digits after the decimal point. So our answer has to have 2 digits after the decimal point, and it goes there. So the final answer is 72.42. Now, I don't expect anyone to be able to just look at this and know what the answer is, but make sure you have some idea. This is a little more than 10 times a little more than 7. So our answer should be a little bit more than 70. You need to check your own work in a test. So if you got an answer here that was like over 100 or below 10, you know you're way off and you need to do it again. Always make sure that you're checking your work. All right, let's move on to another mistake. So the next mistake is thinking that square numbers are negative. So this is how square numbers work. So 0 squared is 0. If you square any other number, the answer is always positive. We know 3 squared is 9. That's easy. It's a positive number. But if you square negative 3, people think the answer must be negative 9. It's not, because squared means multiply by itself. It means multiply negative 3 by itself. And as we know, 2 negatives multiply to give a positive. So if you square something like negative 7 squared is going to give a positive answer. All right, let's move on to the most common mistake in this video. So the most common mistake on this video is using the equal sign incorrectly. I'll explain what that means in a second, but it happens all the time in order of operations questions. So let's look at this sum here, negative 3 times negative 4 squared. There are two operations, multiplication and squaring or raising to a power. Now the I in BIDMAS means index or power. That comes after brackets and before multiplication. So when doing this, my first step, I would need to calculate negative 4 squared, which you know is positive 16. And then I need to multiply negative 3 by positive 16, which is negative 48. This is an example of using the equal sign incorrectly, even though my final answer was right. You see, negative 3 times negative 4 squared doesn't equal 16. In fact, what I've written is nonsense. I've written that 16 equals negative 48. Clearly they don't. They are not the same number. What you need to do is put in all the operations and work down the page. So I need to still put the negative 3 in here. Okay, if I do that, now everything is equal. So it sounds really basic, but you can only use the equal sign when things are equal. So let's look at this one here. So here we do everything in the brackets first, and then we raise to a power. So in the brackets, we have a subtraction and a multiplication. Order of operations means we're going to do the multiplication first. So negative 5 times negative 2 is 10. So negative 13 plus 10 is equal to negative 3, and then negative 3 squared is positive 9. That probably sounded really complicated the way I did it, but this is the way most people write. This statement is complete nonsense. No, this thing here doesn't equal 10. 10 is not equal to negative 13 plus 10. This statement essentially says that 10, negative 3 and 9 are all the same number, which is complete and utter garbage. What we're going to do instead is work down the page and do one operation at a time. So we're going to do the multiplication first. So I'm going to leave the negative 13 alone. So 5 times negative 2 is negative 10. So I've got negative 13 subtract negative 10 squared. So now we're going to add these. Negative 13 plus 10 is negative 3, and we know negative 3 squared is positive 9. So here, when I've used the equal signs, the two things on either side of the equal sign are actually equal. It sounds basic, but it loses kids lots of marks in tests. All right, let's move on to the next mistake. So the next mistake is making arithmetic errors when converting fractions to decimals. So if I have 7 over 8 and I want to convert it to a decimal, it's 8 into 7. It's always what goes on the bottom of the fraction that goes outside. So we go 8 into 7 is 0 times remainder 7. Now people often make mistakes here. They'll say 8 into 70 is 10 times or whatever. If you don't know, count up by 8s. 8, 16, 24, 32, 40, 48, 56, 64. The next one, 72, is more than 70. 8 goes into 70 8 times. 8 times 8 is 64, so there's 6 remainder. 8 goes into 67 times. 7 times 8 is 56, there's 4 remainder. 8 goes into 45 times. Now, because there's no remainder, we stop there. 7 over 8 is a terminating decimal. If I were to do 7 over 11, I go 11 into 7. So 11 goes into 7, 0 times remainder 7. We always have to have decimal point above decimal point. 11 goes into 76 times. So 11 times 6 is 66, and there's 4 remainder. 11 goes into 43, remainder 7. 11 goes into 76, remainder 4. 11 goes into 43, remainder 6, and so on. You can see the pattern. So in exact form, 7 over 11 is 0.63. We put a dot on the 6 and a dot on the 3 because they repeat infinitely many times. 7 over 11 is a recurring decimal. It goes forever, and there is a pattern to it. 7 over 8 is a terminating decimal. So just take care with the arithmetic in these short division algorithms because a lot of mistakes are being made. All right, let's move on to our final mistake. So the final mistake is thinking that fractions are irrational. So just so you know, 1 over 13 actually has a recurring decimal, but it has lots of digits that are repeated, lots of digits in its decimal period. 1 over 13 is 0.076923, 076923, 076923. That repeats forever and ever. But if you put it on your calculator, it may be hard to see that it actually repeats. Depending on the calculator, you might get this answer. And so if you get this on your calculator, you might think, actually, there's no pattern of digits repeated. You might think, okay, it doesn't have a terminating or recurring decimal, it must be irrational. So let me make this clear once and for all. Any fraction with integers like 1 over 13 is always rational. Fractions are always rational. They can always be written as a terminating or recurring decimal. Doesn't matter how complicated the fraction is. 100 over 17, heaps of digits are repeated, but it is rational. I'm going to put it in the R row for rational numbers. 7 over 33. That is rational. I don't need to check its decimal. Fractions are always rational. Whole numbers are also rational. So 5 is a rational number because it's a whole number. Terminating decimals are rational. Recurring decimals are rational. All of them are rational. The only irrational numbers you need to know are the square roots of non-perfect squares. So 5 is rational because it's a whole number, but because 5 is a non-perfect square, the square root of 5 is irrational. The number 2 is rational, but the square root of 2 is irrational because 2 is a non-perfect square. Now, 4 is a perfect square. So the square root of 4 is rational. It's only when you square root a non-perfect square that you get an irrational number. So 20 is a non-perfect square. There's no number that you can multiply by itself, or no whole number you can multiply by itself to get 20. So 20 is rational, but the square root of 20 is not. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.